Okay, so for the last topic of the week, we're going to look a little bit more at different types of nuclear reactions. We've looked at different types of nuclear decay, which, yes, are a type of nuclear reaction, but we're going to zoom out a bit more and see how they fit into other categories. So far, we've only really looked at spontaneous nuclear reactions. What are those? Well, spontaneous means it just happens, right? Nothing has to make it happen. It just is going to happen because the atom or isotope is unstable, right? So it happens in unstable atoms always when Z is greater than, whoops, not greater than or equal to, just greater than 82. So greater than lead, right? No matter what the neutrons are, those are unstable, those will undergo decay. Okay, but also you can have anything be unstable, no matter how many protons it has, if it has the wrong ratio of neutrons to protons, right? Like we said, hydrogen is very stable. Hydrogen 1 is very stable anyway. But hydrogen 7 is extremely unstable. It has a half-life of 10 to the negative 28 seconds. It all just has to do with that balance between the strong nuclear force and the electrostatic force. Now, what we haven't really looked at yet is artificial transmutation, which just means something that would not normally undergo a nuclear reaction is made to do so by some external influence. That external influence, for the most part, as we're going to talk about it, is human caused, but not always. An important thing to note here is that all types of nuclear reactions are exothermic because they don't happen if they're not exothermic. It wouldn't make sense. In physics, things kind of want to turn to their lowest energy state, right? Which means they want to release energy. So again, that just means more energy is released than absorbed. Energy is always a product, okay? Often this energy is a gamma ray, not always, but often. Okay, so just a reminder of what it looks like spontaneous, and let's actually consider the energy given off here and when we write this one out. So nickel 61, beta negative decays producing a gamma ray and a new daughter element. What is the daughter element? So beta negative decay. Let's first figure out what the new element is. So I started with a charge of 28 positive from those 28 protons. I now have -1, so if I'm going to have the same charge, okay, which makes it copper. Conservation of nucleons. I started with 61. The electron, the beta negative particle, doesn't provide any, so this must have, do not forget the anti-neutrino. I remember it's anti because of the negative, because it's beta negative, and the anti sign kind of looks like a negative. Okay. I'm also just going to show the energy here as a gamma photon. You might be saying, what is this gamma radiation now? Well, remember, when did gamma decay happen? It was usually after a beta or alpha decay, right? So we're just kind of putting two reactions into one where, yes, this will be produced and then it will stabilize itself like that. So what is the daughter element? Copper. Okay, so again, why did this happen? Well, nickel was unstable and it just happened. We didn't have to do anything. It just wanted to happen, okay? All right, so there are two main types of artificial transmutation. The first that we're gonna look at is fission, okay? Fission literally means to break, to split up. So a large parent nucleus splits into two or more daughter nuclei and of course releases energy. All nuclear reactions release energy because they're exothermic. Just a note here, I know we said this is a type of artificial transmutation. It is, but fission reactions can also just occur spontaneously. I want you to think about this. A fission reaction is when a large parent nucleus splits into two or more daughter nuclei. Does that sound like something we've done? Yeah, that sounds like an alpha emission, right? A large nucleus emits an alpha particle, which is just a helium nucleus, and then whatever the other nucleus is the second daughter, okay? So alpha decay is technically an example of fission, but it's given its own name. So fission doesn't have to be artificial transmutation. You can have spontaneous fission, especially with really big elements, okay? But when we use that word today, we're mostly going to be talking about artificial transmutation, okay? Now, the other one that is always artificial, it will never happen on its own. You'll see why when we actually talk about it, is fusion, right? If you fuse things, you bring them together. So fusion is actually when two smaller nuclei fuse into a larger one, and again, releases energy because all nuclear reactions release energy. First, let's look at fission. So in artificial transmutation, how humans make it happen is typically by bombarding a large nucleus, roughly with an atomic mass larger than 120, that's where it works best, okay, with neutrons. Why neutrons? Well, a neutron can briefly become part of the nucleus. And as we know, messing with the nucleus, messing with that ratio, you can make something unstable pretty easily. So you make an unstable isotope that will then decay into more stable daughters and release energy. Another reason why a neutron, well, you don't have to worry about your neutron getting repelled by the nucleus. It's neutral. It's not repelled by anything, at least in terms of charge, right? So you're good. You can shoot a neutron there, and it might actually make it to its target, cause it to become unstable, and split into these two daughter nuclei. Now, almost always in a fission reaction, neutrons are also released too. We call them free neutrons. This one is also a free neutron. So one free neutron comes here. In this particular fission reaction, 3 free neutrons were produced in the end. That's basically just a result of these things are getting stable. There's a lot of energy getting released. Things are getting shuffled up. They might as well get rid of these three to even be more stable. These three can then be released just to maximize stability as they go, right? But it's still just conservation of nucleons and conservation of charge. It's just that before we had one thing becoming two or more things. Now we have two things that are going to react to produce, well, more things, more daughters and particles. Okay, where does the energy come from though? Well, we've talked about this before. It just corresponds to the difference in mass between the reactants and the products. How do we relate those things? Mass energy equivalence, E equals mc squared. Do you remember the name for that difference in mass? What's the proper name? Mass defect, right? Okay, so see what I mean? The exact same ideas are at play here, all the same physics principles. It's just now, instead of having something split apart, decay into something spontaneously, we're going to bombard it with a neutron, and that can induce fission. So determine the identity of question mark. How would you do this? Same old physics principles, okay? So we essentially just need to make sure that all the nucleons on charge before is equal to all the nucleons in charge after, right? This side needs to be the same in this side in A and in Z. So for nucleons on this side, we have 235 here, 1 here for a total of 236. And for charge, we have 92 protons, so 92 plus. On this side, we have whatever question mark is for nucleons, 144, and 2 from the 2 neutrons. Be careful, right? 2 neutrons, each of those is 1 nucleon. Charge, 57 protons there, and 0 from the neutrons. Okay, so essentially what we've done is an algebra problem, right? We need to end up with 236 on this side. We can already account for this many, so what's missing is whatever the difference between 236 and these are, right? So the mystery nucleus has 90 nucleons. And how many protons? What's its charge? Well, we started with 92 positive. We already have 57 accounted for. Whatever's left is going to need to come from question mark. And there we go. So this mystery nucleus is bromine 90. Okay, so nothing really different here. It's just now we have not just something falling apart because of spontaneous decay, we're inducing decay with a neutron bombardment. All right, same idea here, okay? Conservation of nucleons, conservation of charge. So we started with 236, can already account for 92 and 141. Whatever's missing has got to be this thing. Okay, I got 3. Now in terms of charge, we have 92 positive charges here. We can account for 36 plus 56. And whatever's left over has to come from question mark, except what's left over, what needs to be accounted for is 0. So you should already probably be thinking neutrons whenever you have artificial fission like this. That is almost always a product, okay? But now we can kind of confirm, okay, so I need something that has 3 nucleons and no charge. What has 3 nucleons and no charge? Well, no charge, it's got to be neutrons. Now what has 3 nucleons that is neutrons? Well, 3 neutrons. So it's not 30N, it's 3 single neutrons, okay? All right, now how much energy would be released in the above reaction? Again, we know it will be released. All nuclear reactions are exothermic. And again, that comes from the differences in binding energies, right? The missing mass will have gone into becoming energy. So there will be some extra energy that needs to be given off. Where will it have come from? Well, there's going to be a mass difference between those two things, okay? So we need to first find the mass defect. We will always find that the products will have slightly smaller mass than the parents because that will allow to expel some energy. Remember, things in nature kind of always things in the universe kind of always like to be in their lowest energy state. So if the products had more mass, that would be more energy, and they wouldn't want to go to that state. They want to go to a lower energy state. Okay, now it says we'll need the data in table 7.5 and 7.6 on page 881. If you do not have your textbook, if you forgot to bring it home or whatever, just send me an email and I can send you a screenshot of these because you will need this not only for the notes, but also for the practice assignment if you're doing those, and even for your summative check-in this week. So you will need these tables. I would post it, but copyright law, okay? So just let me know and I can send you a screenshot of them. But on those tables, you will see you have the masses of many isotopes and also of the subatomic particles to a bunch of sig digs. So to get the mass defect, we need to find the mass of all the parents. So the neutron counts as a parent. So we have a neutron, that's one of the parents, plus the mass of uranium-235. Okay, we need to figure out what the difference is between that and the mass of this. So the mass of our daughters, and 3 times the mass of a neutron, because one of our products is 3 neutrons. Okay, and whatever the difference is between those, that mass will have been converted to energy. So on page 881, the masses are given in atomic mass units, okay? Just find your mass defect in atomic mass units and then convert that into kilograms. You could convert all of these masses into kilograms, but that's way more work, right? Just get the mass defect in atomic mass units and then convert that to kilograms. So I got that the mass defect was, okay, that in atomic units. Now let's convert to kilograms. Okay, so now we know the difference in mass between the parents and the products. Where did the mass go? Well, it was converted to energy through Einstein's equation. And we are actually allowed 7 significant digits here because the smallest number of significant digits we have is the mass of a neutron, and that is given to us with 7 sig digs. Okay, so that's the only numbers we've done calculations with, so that's what limits our precision. And that's how much energy would be released, which might not sound like a lot, but remember, this is just from one atom undergoing fission, right? For one atom with a mass of roughly 235 times the atomic mass unit of times 10 to the negative 27, that's a lot of energy, right? That's times 10 to the negative 11 when you're talking about a mass on the order of negative 27. That's not bad. An atom, there are trillions of atoms in just a handful of uranium, okay? So there's a lot of power in there. And we start to talk now a little bit more about the mechanics of how these nuclear reactions actually go down. You might even get a deeper appreciation of the amount of power at play here. Okay, so I want you to just think about something for a sec here. How did we start this fission? What did we have to do to uranium? Well, we had to bombard it with free neutrons, right? Free with an F, right? But hang on, what did we produce? We produced free neutrons. Now, is this uranium just sitting all by itself? No, right? It's an atom it's next to billions of other uranium atoms. It's very hard to isolate just one atom of anything. So it's probably sitting in a block of uranium surrounded by trillions of other uranium atoms. And it just sent out 3 free neutrons, kind of like the one that just caused it to undergo fission. Do you see where this might be going? Oh my goodness. Okay, so those 3 neutrons that are produced in the fission reaction can now go meet other uraniums, and they might trigger fission in those, right? We get a chain reaction. And so this neutron comes in, causes this uranium to undergo fission, split into 2 daughters and 3 neutrons. And now those neutrons go hit, splits into 2 daughters and 3 neutrons. Those 3 neutrons are now free to go hit more, and then more, and then more. So you have some sort of exponential growth here, okay? To kind of get an appreciation for this, let's think about it. So after 10 reactions, maybe not 10 reactions, right? Because technically this is already 1, 2, 3, 4, but 10 like generations, right? So if this is a generation of reactions, that's a generation of reactions. It's asking us, after 10 generations of reactions, how many atoms will be splitting if all 3 neutrons initiate fission each time? Well, let's just think about this. So after 1, you just saw you could have 3 more fissions be initiated, right? 1 fission could cause 3 more to occur. Now, after 2 fissions have occurred, well, if each of those 3 now go on to cause another reaction, we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9 fission reactions occur. And each of those 9 are going to result in 3 neutrons being released. So in the next iteration, we're going to have 9 fission reactions that each produce 3 neutrons. And if each of those 3 produce a new fission reaction, we have 9 times 3, 27. Now, each of those 27 are going to produce 3 neutrons. If each of those, we're going to have 27 times 3, 81. Those are all going to produce 3 neutrons. So if 3 times 81 reactions happen, we're going to have 243. Do you see the pattern here? We're doing powers of 3, right? Because each time we're multiplying by 3 for the potential reactions that can now occur. And then that gets multiplied by 3 and multiplied by 3. So we had 3 to the power of 1, 3, 3 to the power of 2, 9, 3 to the power of 3, 27, right? So by the time we get to the 10th generation of reactions here, we're going to have 3 to the power of 10 because it's been 3 times 3 times 3 times 3 times 3 over and over and over again. 3 to the power of 10 is 59,049 potential reactions that are happening then. Okay, that's just on that generation, not even adding all the ones that came before. That's only 10 times later. That's not that much, right? So you can see how this can get out of control pretty quickly. You have exponential growth of the energy being put out. Now, just some kind of definitions that we have here related to these nuclear fission reactions, okay, these chain reactions. So when exactly one freed neutron goes on to initiate one more reaction, so for every one, so when you have a fission reaction, it makes one neutron, and then that one neutron goes on and makes one more fission happen. One reaction is just causing one reaction, right? And so the energy getting output is not growing, but it's not shrinking, it's just staying the same, right? You got one reaction, one reaction, one reaction, one reaction, one reaction, all putting out the same energy, okay? So every second, you're always going to be getting the same amount of energy out, right? It's just this self-sustaining cycle of reaction causes reaction causes reaction, not reaction causes 5 reactions, causes 25 reaction, causes 125 reactions, okay? So the reactions we would say are just self-sustaining. What's the word we use for that? We say the reaction is critical. It can keep itself going, okay? Now, when more than one freed neutron goes on to initiate more reactions, a better way of saying that is, on average, one reaction leads to more than one reaction. That was what we saw in the previous diagram, right? Because one reaction was actually causing 3 more reactions. And then those 3 reactions were actually causing 9 reactions. So we were getting exponential growth. The amount of energy being released increased exponentially. So it's not critical. It's not just sustaining itself. It's actually growing. So super means above. So we would say it is super critical. It's above critical. It is growing. Now, on average, when less than one freed neutron, so say you have 2 reactions and maybe one of them causes another reaction, but the other one, the neutron just kind of fizzles away or gets absorbed, it doesn't actually cause a new fission, okay? Well, then say the reaction sub means below, right? Sub-zero temperature is below 0. The reaction is subcritical. It's below 0. So eventually what's going to happen is if for every one reaction, you're not even getting one more reaction out of that, right? Like say for every 2 reactions, you're only getting 1 reaction out. Well, that's going to go downward, right? Eventually, you'll get to the point where you have no reactions occur. If you keep it subcritical, the reaction will eventually peter out because fewer and fewer reactions are going to be happening. So what's the application of all this stuff? Well, this is how we power nuclear reactors, which is what nuclear power is, right? Nuclear power is generated at a nuclear reactor. So when you first start it up, you got to build it up to the point where it's putting out enough energy to actually power what you need to do, right? So you say, okay, the city that we're going to power uses this much energy every hour. So we need to get to the level where these nuclear reactions are putting out that much energy every hour, right? And then we'll just keep it there. But to get up to that level, you need to first make it super critical and build up that necessary energy output. Get the chain reaction going to the point you want it to be at, okay? But then you don't want it to keep going because then you're going to have too much energy. You're going to have a dangerous situation there, right? So then you lower it and just sustain it at critical levels. You say, okay, the city needs this much every hour, so we'll find the point where it's critical. It's just sustaining itself at that level. And there we go. We're good. We have the energy we need. It's just keeping itself going, okay? Now you might be saying to yourself, well, how do we control that? How do you have control over whether or not the reaction goes supercritical, subcritical, or stays at critical? Well, remember, what's going to cause that chain reaction? Neutrons freed in the previous reaction, right? And then they go on to cause more fission and free more neutrons. If you can cut that off, if you can stop those neutrons from going on to cause a new reaction, then you've mitigated the criticality here, right? So how do we do it? We have neutron absorbing materials. So carbon is a good neutron absorber. Heavy water is a good neutron absorber. What's heavy water? It's just water that instead of H2O, I mean, it's still H2O, but it's not just H with one proton. It's something we're going to learn. It's called deuterium, which is just hydrogen 2. It has a proton and a neutron. That's a very good neutron absorber. Okay, that's the one that can do the Canadian nuclear reactor in Ontario. That's the one that uses is heavy water as what they call a moderator. It's just something that allows you to control the rate of fission and let the chain reaction happen at the rate that you want it to. Okay, so essentially, if it goes subcritical, you back off with the neutron absorbers, and that increases the rate. So you get back to critical. If it starts to go supercritical, well, you just put the neutron absorbers further down into the reactor to absorb more neutrons, and therefore slow down the rate of the chain reactions, right? Okay, so for a visual, here's a single fission. Okay, here's some more. You see you get the chain reaction there. Those neutrons go on to cause other fission events. And then we can crank it up a bit here. You can see it can get a lot of energy pretty quick. And then here is just the idea in a nuclear reactor. So notice the power output on the right there, right? Kind of trying to adjust to keep it at a consistent level, not letting it go too supercritical or too subcritical because then it'll die out. I actually do accidentally let it go too subcritical and it pretty much dies out. But then you can always just fire more neutrons. How does this all actually lead to you being able to turn on the lights at home? Well, the same way that in Alberta, burning coal leads us to be able to turn the lights on at home, right? As we said in Unit 2, pretty much all of our electricity comes from making a magnet spin, right? The generator effect. So changing magnetic field induces current. And in fact, the way that nuclear does it and the way that coal does it is the exact same. In coal, you light the coal on fire, burn it, boil some water, and then use the steam to turn a turbine, which is magnetic, and then induces a current, and then that allows you to flick on the lights, right? In nuclear, you just use the heat from the nuclear reactions to, again, boil water, generate steam, turn a turbine. Everything from then on is the same. So heat given off, used to boil water and turn a turbine. So if you're still not convinced about the incredible amount of power that can be harnessed in a nuclear reaction, okay, here's some stats. So uranium fission per gram can release about 8,000 times more energy than fossil fuel combustion. So if you have 100 grams of coal and 100 grams of uranium, you're going to be able to get 8,000 times more energy out of that same amount of uranium. It is much more efficient when it comes to producing energy. In fact, nuclear reactions are so efficient that despite the fact that there is much less uranium in the world, right, that's a much rarer substance, and our reserves of it are way smaller than our fossil fuel reserves, the potential energy that is in that uranium that we could use to power stuff, there's actually more in the uranium than there is in all of our fossil fuel reserves. Even though there's way less of it, we could actually power ourselves for longer on just the uranium that we have than on the fossil fuels we have, even though there's way less of it. And anywhere when we were writing our reactions, did we put carbon dioxide down as a product or methane or any of those? No, right? All of these processes happen with zero greenhouse gas emission. Okay, now to be fair, right? The energy production itself has no greenhouse gas emissions. Nuclear reactions don't produce greenhouse gases, carbon dioxide, anything like that. The mining of uranium might still rely on the fossil fuel industry, and that would produce carbon dioxide. I don't want to be misleading and say, oh, the nuclear industry has zero emissions, okay? But the actual process of generating the energy, yeah, it has no greenhouse gas emissions compared to combusting a whole bunch of coal to turn a turbine, which has, well, literally tons of greenhouse gas emissions. So is it all sunshine and rainbows? Well, not quite. A downside, the big one that will come up with nuclear power, okay, uranium fission in particular, is that some of the byproducts are themselves radioactive. So they are hazardous materials that need to be handled carefully. Not only that, they have very long half-lives. So before they decay to a level where they're not harmful anymore, we're talking like thousands of years. So you do need to be able to find somewhere to store them and to store them carefully for a long time. That can be done. We have facilities that do that, but it is a problem. It's definitely a downside to nuclear energy. Another big downside is honestly that people are kind of scared of nuclear energy, right? I think it is one of those things where the more you learn about it, you realize the less scary it is, right? Some of the things that pop into mind, like Chernobyl and Fukushima, have to do a lot with mismanagement of those facilities, particularly Chernobyl. There was a lot of corners cut, a lot of safety precautions not taken that would be pretty easily mitigated with some oversight. But I do want to talk a bit about current research in nuclear power on an element called thorium. Okay, now thorium can be made to react in such a way where the radioactive byproducts are not only present in much smaller quantities, so you get about 2% as many radioactive products as you would in uranium fission with thorium fission. Okay, but the kicker is that they also decay to safe levels much faster. They have a much smaller half-life than the uranium radioactive products. So over long term, you don't have to store it as long. Like I think 100 times shorter amounts of time do you have to worry about this byproduct. To kind of put some numbers on it, it's been estimated that just 1 ton of thorium could produce as much energy as 200 tons of uranium, or 3,500,000 tons of coal, right? So there's some pretty incredible potential energy that can be tapped into in nuclear power. So nuclear power involves chain reactions, yes, but controlled chain reactions where you use a neutron absorber to keep things critical, right? And if they start to go supercritical, bring it back down. If they go subcritical, well, let it grow a bit. Now, what about when it goes out of control? What if you allow it to grow exponentially? Well, then you've got the source of power for a fissile nuclear bomb, right? You want very quickly a lot of energy produced, so initiate fission in a bunch of uranium and let it go. And you have a fission bomb. So like any great source of power, it can be used to do a lot of damage as well, right? Unfortunately. Also, unintentionally, you can have a nuclear meltdown. That's what happened at Chernobyl. It went supercritical, mistakes were made, and the chain reaction was not controlled. That led to a steam explosion when all of the energy kind of blew into the water that was going to be boiled to turn a turbine. And that explosion sent radioactive material everywhere. Okay. So it is something, obviously, like everything we need to be careful with, but when done carefully, when done right, It's a pretty incredible source of power. Okay, when a metal plate of zinc is bombarded with neutrons, one is absorbed. One is absorbed. This results in the formation of calcium-40, neon-23, and other things. So what are the other things? Okay, let's start with the products because they told us those, or some of them anyway. So we're going to have calcium-40, okay, neon-23, and other stuff. Okay, now I want to come back to the zinc here. Important note, okay, they didn't say which isotope of zinc. When that happens, always, okay, go to your periodic table and round to the nearest whole number for the atomic mass, okay? So zinc has an atomic mass of 65.41, so we're going to round to 65. Okay, and then the other thing the question told us is that it was bombarded with neutrons, right? One is absorbed, so add a neutron as a reactant, which is just one nucleon with no charge. Okay, and physics principles number 7 and 8, we got to figure out how we keep the nucleons and the charge constant on both sides. So what is missing here that would allow that to be true? So we have 66 nucleons on this side. Right now we have 63 nucleons over here. So we're going to need something with 3 nucleons. I'm just going to look at charge first. Right now we have 30, and then 20 plus 10 is 30. Okay, so the charge is actually good. So whatever is here, it has no charge, right? Now you can see what I mean. Okay, so yes, we have something that's going to have a total of 3 nucleons, right? But if it has 0 charge, well, the only thing with 0 charge is, besides a neutrino, which it's not a neutrino because a neutrino's not a nucleon, so it must be 3 neutrons. So what else is produced? 3 neutrons. Okay, now is a supercritical chain reaction possible? So what's that really saying? It's saying, can this reaction end up producing more than one reaction in the near future, right? Well, can it? It took 1 neutron to get it started, right? It hit a zinc atom. That zinc atom's back next to a bunch of other zinc atoms, and now it just sent out 3 free neutrons. So what's to stop those from making history repeat itself, right? So from this one reaction, we're potentially looking at now 3 more reactions. Well, that is absolutely supercritical. Yes, it could cause up to 3 additional reactions. So certainly it's possible. Might not do that, but it is definitely possible. Which really 3 is arbitrary. It's just that it's more than 1, right? Okay, very similar question, but a slight difference here. Now the zinc plate is going to be bombarded with neutrons. So again, we have rounding to 65 because that's what's on the periodic table and they didn't give us an atomic mass. But we're going to make slightly different daughters. We're going to make calcium-42 instead of calcium-40, but still neon-23. What else is produced? So how do we get this thing balanced? Well, we have 66 nucleons, and here we have 65 nucleons. Okay, so whatever's missing is only 1 nucleon. Charge, we have 30 positive charges here. We have 30 positive charges here, so this thing must not have a charge. What is 1 nucleon with no charge? Well, that's basically the definition of a neutron, right? A nucleon with no charge. So what else is produced? 1 neutron. Is a chain, whoops, that should say a supercritical chain reaction. Now, generally, chain reaction kind of implies supercritical, but it's just added in anyway. Could it? What's the best this could do? What's the most efficient this could possibly cause? The best this could do is critical, right? Because it's only making 1 neutron. And as we've seen, it takes 1 neutron to get this reaction going. So this 1 neutron might go cause this to happen again, but it can't make more happen, right? For every 1 reaction in, we get 1 reaction out. So it could sustain itself at best. At best, it could be critical. Critical at best. Okay, that kind of wraps up fission. Moving on to fusion now, the other type of artificial transmutation. Now, fusion is never spontaneous, and you'll see why when we talk a little more about it. So under extreme pressure and temperatures, in fact, that's it. It only happens under extreme pressures and temperatures. 2 or more nuclei can be fused together, hence the name fusion, into a heavier element, releasing a lot of energy, at least a lot of energy for the mass that goes in. Okay. Now, quick side note before we go on, these are important to know. It's going to assume that you know what these mean. In fact, if you look right now on page 881, they don't even call it hydrogen 2 or hydrogen 3. They just call it deuterium and tritium. If it just says hydrogen, you can assume it's hydrogen 1. It's sometimes called protium. Honestly, more often they just call it hydrogen. So all they are is isotopes of hydrogen, okay? So if you have a neutron and a proton, still 1 proton, so you're still hydrogen, but we call that deuterium, okay? Dew meaning 2, like deuces, right? Here, 2 neutrons, 1 proton, so 3 nucleons total. Try like a tricycle, tritium, okay? So do not use the mass of hydrogen for the mass of deuterium or tritium if you're using that table on page 881. Okay, so here's an example of a fusion reaction. You have, what's this called? Deuterium, right? And what's this? Tritium, hydrogen with 3 nucleons, making helium. Hey, an alpha particle, right? And a neutron and energy. So an example of writing out the nuclear reaction for 2 hydrogen nuclei combined to form deuterium. Again, if it just says hydrogen, assume that's hydrogen 1, okay? So we have, how many nucleons are there in a hydrogen nucleus? Just 1, right? Just that 1 proton. So what's its charge? 1. And we have 2 of them reacting to form deuterium, which is just hydrogen, but with a neutron as well. So 2 nucleons total. Still good old hydrogen. Okay, this is a good one for thinking about what must be produced. Okay, so it's not always going to tell you what kind of decay it is. You might have to think. We've got 2 nucleons. 2 nucleons. So nucleons are already balanced. Okay, but we have one charge for a total of 2 plus on the reactant side. So we need to somehow add a positive charge over here without adding a nucleon. So a proton's not going to do it. What is something we know that has a positive charge but is not a nucleon? Well, what comes to mind for me is a positron or a beta positive particle. Okay, and then whenever a beta positive particle is produced, you could safe bet that a neutrino will be produced. So how do we answer this question? Okay, because this is a general skill to have. So which physics principles were we following? The same ones we always follow, right? Conservation of nucleons. We had to think about, what do I use to make sure nucleons are conserved? What particle can fill in the gap that we have here, right? In this case, it was a beta positive particle. Might not always be, but that's how you should be approaching these. So we use physics principle number 8, conservation of nucleons, to find the top numbers, right? Or to find the particle that would satisfy the top numbers. And then we use physics principle number 7, conservation of charge. When do we use that? Well, to satisfy the bottom numbers, right? To make sure that the charge on here was the same as the charge overall over here. And more specifically, to find the particle that would allow that to be the case. Right, now using those unrounded long numbers on table 7.5, 7.6 on page 881, calculate the energy released during this reaction. So where do you think the energy is going to come from? Well, I have a sneaking suspicion that the mass of these is going to be smaller than the mass of these. Now, before we get into it, you might be saying, oh, we got to include the mass of a positron. Ooh, I don't know the mass of a positron. Yes, you do. Okay, it is on the back of your formula sheet in units of mega electron volts per c squared, so you could get it in kilograms, but you can also remember that what is a positron? It's an anti-electron, right? It's the antiparticle of an electron. And antiparticles have the same mass, they just have opposite properties when it comes to things like spin and charge, right? So it's the exact same mass as an electron, if you can remember that, it's just got the opposite charge. Okay, mass of a neutrino, if you're wondering what that is, this is just kind of something to be remembered, honestly. A neutrino is tiny, 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 okay? We actually thought it was maybe massless for a long time, but then we realized it wasn't traveling at the speed of light, and anything without mass must travel at the speed of light. That's kind of a fundamental tenet of relativity. And so we found out that it does have a mass, but it's about 500,000 times, by our best estimates, smaller than an electron's mass, which is already tiny, okay? So we're looking at very, very small mass for a neutrino. Essentially, you can ignore it. It won't make any difference. So first we'll find the mass defect, and then we'll know that difference in mass must have been converted to energy. So our parents are 2 hydrogen 1s. Our products are a deuterium and a beta positive. And using the values on page 881, just plugging in. Okay, and in atomic mass units, I got, and then converting that to kilograms, I got, okay. So now I know the difference in mass. Where did that mass go? Well, it was converted to energy, related by Einstein's equation. I got, and yep, that's the sig digs, right? We get 7 sig digs to work with here because we use the mass of a beta particle, which is given in the book to 7 sig digs. The other ones are given to 8. Okay, so this fusion, it's pretty incredible, right? We're taking 2 elements and fusing them together into a new element. So just a kind of a note here on how we got to where we are. This is how every single element in our universe was made. Okay, every single one of them. Well, besides the really exotic ones that we have to make in like the Large Hadron Collider or something, right? We can synthetically make some elements, but for the most part, it came from this process. So when the universe first began, okay, the first element to ever form was hydrogen. Well, that makes sense because all that had to happen to make hydrogen was a proton and an electron needed to become bound to each other, right? Which actually did take a while to happen. There was a long time where that hadn't happened yet. There was literally no atoms. It was just free protons, free electrons. There was even a time before that where protons hadn't formed yet. But anyway, eventually in some places, enough hydrogen started to kind of group together, right? Because of gravity. So this hydrogen with mass started to group together, coalescing into a ball, okay? Now the balls of hydrogen got bigger and bigger and bigger as they collected more, they attracted more hydrogen to themselves, growing, right? Eventually it got massive enough that the gravity was so intense, so pressure that in the middle, in the cores of those big balls of hydrogen, there was enough pressure to fuse two hydrogen atoms together, and that released energy. That continues to happen. That gravity continues to squeeze hydrogen atoms close enough together that they fuse. That energy is produced. And there you go. You have the birth of the first star. And along with that, you've also now created the second element ever, right? You fused two hydrogens together. Well, hey, putting two hydrogens together, you just made helium. So now there are two elements in the universe. Wow. Okay. And so that's what a star is doing. That's what our sun is currently doing. It's fusing hydrogen into helium. And that's what most what we call main sequence stars are doing for most of their lives. Towards the end of their lives, stars start to run out of hydrogen to fuse. They have fused all the hydrogen into helium, and so they say, okay, well, we're running out of fuel. Let's start fusing the helium together. Why not, right? We got the gravity to do it, so they start taking helium. And I put 3 down there because that makes something interesting, but really you can do different combinations and make different things, right? But you fuse 3 helium together, and you've got now 6 protons. Hey, that's carbon. Congratulations, you've made carbon, the building block of life, right? And with all these different combinations of larger and larger nuclei, you can cook up all of the elements in the cores of stars until you get to iron. Everything up until iron was cooked in the core of a star over millions of years throughout that stellar evolution. Why up until iron? Well, iron can be fused together, okay? It's not and nothing special about iron. The thing is, though, you have to put more pressure in. Iron is actually the most stable element, so you have to put more energy into iron to make it fuse into something else. Then you are actually going to get out of that reaction. So it's not that it can't do it, but if it tries to do it, it's not going to burn anymore. It can no longer be used as fuel, right? If you put gas in your car that takes more energy to burn than it produces when it burns, your car is not going to go anywhere. So the same thing happens to the star. This is the beginning of the death of the star, okay? The fuel in it is no longer supporting it. By the way, supporting it against what? Well, a star's entire life is basically a battle against gravity, right? Gravity is trying to crush it in so close, and then fusion kicks in, and that energy pushes back out and says, no, 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 I've got energy here to fight this gravity, okay? But now it's starting to die. It's starting to lose the battle against gravity. Now, okay, you might be thinking, well, iron, that's only atomic number 26. How do we get numbers 27 all the way up to 118 and potentially beyond? Because there's no reason for sure that the periodic table ends at 118 like we have it now, right? Well, truthfully, some of those we have to make synthetically, but most of them not, right? Most of them exist naturally. So where do they come from? All of those elements that we have larger than iron, they come from pretty much one specific type of event. In the most massive of stars, that moment when the engine shuts off, when fusion stops producing energy because you're fusing things that net use up energy and not net produce energy, it can result in what's called a core collapse supernova. So the core collapses, it's no longer producing energy. Okay. Now, without that happening, gravity basically takes over. The star goes into free fall. We actually call it the free fall time. We can calculate it, right? It's essentially at the speed of sound. We call it the free fall time. Okay. And the outer layers of the star collapse into the core, pulled in by gravity with no fusion to support against it. So without the energy from fusion powering it, it collapses in on itself rapidly. Now, suddenly, think about that. You have all these outer layers of the star, all that potential gravitational energy coming in and crashing into the core. Well, in one last kind of blaze of glory, the star makes one last dying, passionate contribution to the universe, right? In that moment where all of that energy comes crashing in on the core and those extreme, extreme pressures and temperatures, fusion is suddenly reignited, briefly, but powerfully. And in that moment, in that little time there, every single element that exists in the universe, heavier than iron, is made. Enough energy is provided to fuse things, because you have energy to spare, right? Things that cannot support the star, but you just put enough energy and they're going to fuse anyway, everything is produced. Not only that, but now that energy is going to blast back outward in what's called a supernova. These supernovae can be brighter than galaxies. That's the amount of energy we're talking about here. And so that supernova blasts all those newly made elements that didn't exist before out into the universe to be spread into interstellar space, literally just outwards towards other stars, right? Even the ones that aren't going to go supernova, the instability at the end of a star's life where it's going between, okay, now I'm fusing oxygen, oh, now I'm fusing silicon, right? There's kind of a whoop, whoop, whoop that's happening from gravity's winning, oh, new fusion, right? Oh, gravity's winning, oh, a new type of fusion. And so that kind of instability causes it to sort of shake off its atmosphere and its outer layers into space. And so those elements like iron that it's been cooking now for a long time in the last phase of its life, that iron is going to get brought out into interstellar space, off drifting through the interstellar medium. And maybe, just maybe, on a very off chance, that iron will find some other star and it will get pulled into its gravitational influence and it will start to orbit, and little pieces of iron will start to meet up and they'll start to coalesce into a hot ball of mostly iron. And it will be hot, but it will cool and it will cool, and maybe on some off chance a comet will collide with it and now water will be there, and then maybe on some other off chance some dying star, some other star somewhere will blast some carbon out into the universe, and that will land on this little ball of hot iron, and that carbon will start reacting with hydrogens and oxygens and nitrogens, and it will start to form molecules, and these molecules might start to join together into more complex molecules and start to form proteins even. And these proteins start to work together in more complex structures to form something that seeks out energy, a cell. And suddenly you have life. And then if you leave that life for 4.5 billion years, evolution will take its course. And maybe, just maybe, one day that life will be sitting watching a video talking about how it got to where it is now. And remember its origins in the core of some star that gave its life so that it could be here. Okay, so you may have heard it said that we are, all of us, stardust. It's absolutely true. There is no carbon, which is we are carbon-based life, without fusion happening in the core of stars. Okay, so our star is not in the phase of its life yet where it burns helium. When that happens, our sun will go red giant and swallow up to the orbit of Mars. But don't worry, we got about 4.5 billion years till that happens. Okay, the reaction at the center of our sun is of tritium with deuterium to form helium-4. What else is formed? So this is what's happening in our sun. This is why we're all here, amongst many other reasons. So tritium, that is just the isotope of hydrogen that has 3 nucleons, right? So hydrogen, so 1 proton. Deuterium, isotope of hydrogen with 2 nucleons. And we're making helium-4. So what's missing? We've got 5 nucleons we have to account for after this reaction, but only 4 here. So we're going to have something that's got a nucleon, but we have 2 plus charges. We have 2 plus charges. So whatever this thing is that's a nucleon can't have a charge. Sound like something to you? That is a neutron. Okay, so just a quick comparison here to wrap up on fusion versus fission. Which one produces more energy? Well, per mass that you put into it, by far fusion, right? It makes sense. To get fission happening, you need a huge nucleus that's kind of unstable, kind of prone to decay if you can just stick a neutron on it or something, right? So you're looking at 235 atomic masses roughly for uranium, and you're going to get out some energy. Okay, don't get thrown off by this. I know this makes it look like, oh, this 0.2 times c squared and 0.02 times c squared, you're going to get less energy. Yeah, sure. Per reaction, you're going to get less energy out. But per nucleon, per mass, you get way more energy out of fusion. Fusion is a much more bang for your buck reaction. So comparing the two in terms of energy, fusion, much more energy than fission, per nucleon, I should say, per nucleon. Now, you might be saying to yourself, well, then how come we use fission in all of our nuclear reactors? Well, fission is a lot easier to make happen, okay? Why is it easier to make happen? Well, one of the big reasons is that the neutrons don't care. They'll go into the nucleus and then make fission occur. right? Compare that to fusion. What are you trying to do? You're trying to force two hydrogens together. Those are two protons. They really don't want to be together. The neutron has no problem. You take a gun and just shoot them at the nucleus, right? They'll do that, whatever. Protons don't want to fuse together. You're fighting what they want to do, okay? Don't forget, where does fusion happen? In the cores of stars mostly. We have made it happen on Earth, okay? But it's difficult. It mostly happens in stars where the temperatures and pressures are extreme, and that is an understatement when I say extreme, okay? Reproducing these conditions on Earth requires a lot of energy. Not that we can't do it, but making those extreme pressures and temperatures, we have to put so much energy into making that happen that the fusion that ends up happening ends up not even making it worth it. We get less energy out than we put in. Now, don't take that and say, oh, fusion is endothermic. No. Fusion is exothermic. But getting to fusion can require a lot of energy. Once fusion happens, it always releases energy, but getting there requires a lot, okay? Now, research is active in this area, and we actually have, I think it was in 2014 for the first time, gotten a little bit more energy out than we put in. Now, it wasn't much, okay? Not to the point where you can say, okay, fusion power is ready, but maybe on the horizon, okay? Maybe in our lifetimes we will see widespread fusion reactors. The other reason fission is easier is because it's not only easier to get going, it's easier to sustain because you can take advantage of the chain reaction, right? You start it and you say, okay, neutrons, you go do your thing, you cause more reactions, I'll settle you down if you get too much using carbon rods or heavy water, right? Neutron absorbers. But you don't have to keep constantly supplying that energy like you would for fusion, right? If you let that pressure stop, fusion stops. Not the case with fission. In fact, you kind of have to be careful that fission is able to stop, right? It's kind of the opposite of fusion where you have to keep it going. Fission, you got to make sure you can stop it if you need to. Okay, comparison for hazards. Fusion by far takes the cake on this one, right? Remember, as we said, the big problem with fission, the big problem people have with that is that it produces radioactive products. Hey, what's produced in fusion? Yeah, helium. The stuff that you can suck out of a balloon at a kid's birthday party and make a hilarious voice, right? You can literally breathe it into your lungs and nothing will happen. It's a completely noble gas. It's inert. It's not going to do anything. In fact, did you know the Earth has a helium shortage crisis? We're going to run out of helium. So producing it this way would actually make a very useful byproduct for us. Okay. The other reason fission is dangerous, we kind of already covered, it can lead to runaway chain reactions if it's not properly moderated. So what are they used for? How do we compare them in terms of usage? Well, it's a sad reality that whenever we have this kind of power at our hands, unfortunately, humanity always seems to find a way to weaponize it, right? It's another unfortunate reality that some of our biggest scientific advancements also come from finding ways to use it to, well, do harm to one another, right? In fact, so much of our advancement of nuclear knowledge came from World War II, where a bunch of physicists were hired to research this to see if it could be weaponized, right? In fact, a lot of the physicists that worked on the Manhattan Project, which is the one that ended up developing the atom bombs that were dropped in Japan, would go on to have it haunt them for the rest of their lives. They would regret it. A lot of them went on to form organizations of physicists and scientists to speak out against ever using science for this kind of destruction ever again. It would weigh on a lot of their consciousness. So the societal side of physics can't be ignored either, right? We have to consider the societal lens that science operates within. Okay, so both, yes, are used for bombs. The bombs that use fission are known as fissile bombs. Bombs that use fusion, you might have heard this before, they're known as hydrogen or H bombs because that's what they're doing. They're fusing hydrogen. They're also sometimes called thermonuclear. Thermo meaning heat, nuclear meaning from a nucleus, right? So heat from a nucleus. Now you might be saying to yourself, hang on, we can do fusion in a bomb, but we can't do it to power our cities. Well, the difference is control, okay? Remember, it takes a lot of energy to get fusion going. And the way we do that is with a fission bomb. We basically have a fission bomb sitting next to the fusion bomb that's ready to go off. And when all the energy from that fission bomb goes, it can trigger fusion in the hydrogen. And that is how an H bomb is made. So again, so far only fission is used for nuclear reactors. And again, it's just because fusion is still a problem because we are not able to efficiently put the nuclei together. It takes too much energy to put them together, which costs too much money. And we end up not getting much energy out of it anyway compared to what we put in. Okay, that wraps up topic 4. If you're looking for practice with this stuff, try the topic 4 assignment in the Google Classroom or agenda. And if you're feeling good about all the stuff this week, if you've come to me with any questions you have, then go ahead and you can do the summative check-in for this week. Okay, have a great weekend.